calculations that we were interested was the dew point pressure for an ideal gas. We saw how to calculate the quantities and composition of gas and liquid in the two phase, how to find the bubble point pressure of the ideal liquid solution, and now if we want to do the calculate the dew point pressure of the ideal solution, the we are going to use the equation for the summation of the liquid. So summation of the liquid, I know it's equal to 1. And I know if the pressure is equal to dew point pressure, that's the pressure at which the last droplet of liquid goes to the vapor. So practically I don't have any liquid. So NL becomes equal to 0. So if NL is equal to 0, then Ng becomes equal to the total number of moles of the mixture. So Ng cancels with N, and then at the condition where the P is equal to dew point pressure, PD, and I know the PD is a constant number, so it can come out of the summation, and then the PD becomes 1 over summation of Zj over PVJ. So for ideal solution, it's very easy to calculate the dew point pressure and the bubble point. In the case of bubble point pressure, the composition of a mixture is given, so PV was simply the summation of Zj times PVJ. I will go and I read the vapor pressure of each component at the temperature given using Cox chart, and then multiply by Zj, sum them up, that's the bubble point. In the case of dew point, exactly like how it shows in example 12.3, again, the composition is given. I can find the vapor pressures, the PVJs at a specific temperature given using the Cox chart. Then the PD is simply 1 over summation of Zj over PVJ. So Zj is given, Zj over PVJ I can calculate, I can sum them up, and 1 over that is my PVJ, is my PD, the dew point pressure. So it's very easy to calculate the bubble point pressure and dew point pressure of the ideal solution. So now that we understand this, we want to move and see how we can calculate these for the real solution. For the real solution, the problem is we need to have a good initial guess for the bubble point pressure and dew point pressure calculation. And we're always going to use this the bubble point pressure and dew point pressure that can be calculated using ideal solution, okay, as an initial guess for the real solution calculations. Okay, just remember that. But in the case of real solution or non-ideal solution, we know there were like a couple of problems regarding not being able to have the methane as a liquid in regular temperatures and all that. So what we are relying on series of experimental procedures which have been done, and people they have come up with the coefficient which is called K equilibrium ratio. Okay, with this K equilibrium constant, okay, or K equilibrium K factor or K equilibrium constant, we can modify the equations that we develop for ideal solutions such that it works for non-ideal solution. This K, even though it says the K equilibrium constant is not actually a constant number, it's a function of composition, it's a function of temperature, it's a function of pressure, and it's also a function of a pressure called convergence pressure. Okay, in the next lecture we are going to visit the convergence pressure and see what that means. But for now, let's assume the convergence pressure that has been used at the end of the book for the tables is valid for our examples. Okay, but this K value is a function of composition, temperature, pressure, and the convergence pressure. So it's defined as, it can be written as Yj over Xj, but we know that it's not equal to that. Okay, it's going to replace the Yj over Xj in the equations 12.8 and 12.9. So if we go back to our equations 12.8 and 12.9, okay, to simply convert this to ideal to the real solution, what I would do is I'm going to replace the PVJ over P by K, because remember, if go back one more time, so Yj over Xj was equal to PVJ over P, and I know PVJ over P is equal to K, is equal to the K equilibrium constant. So I'm going to replace PVJ over P by K in equation 12.8 and 12.9. So if I do that, I would have the summation of Xj being equal to the summation of Zj over 1 plus Ng bar times K minus 1, Kj minus 1. Okay, And for the gas, again, the summation is Zj divided by 1 plus and L 1 over Kj minus 1. Okay, so remember PVJ over P can be replaced by Kj. So if I do that, then I will have the equations. I can actually simplify this by dividing denominator and denominator by n, and then I can have equation 1217 and 1218. So in the case of real solution, the equations that we are going to refer to is the equation 1217 in the case of mole fractions of the liquid, and 1218 in the case of mole fractions of the gas. So if your final exam is to find the composition and quantities of the gas and liquid equilibrium at a given pressure and temperature using real solution, then you refer to equation 1217 and 1218. In these equations, let's say in 1217, which says the summation of xj being equal to 1, the summation of mole fractions in the liquid being equal to 1, the Zj is given. That's a mixture, that's a composition in the mixture. That's given. Kj, for every single component, I can read the K equilibrium constant from the graphs given at the end of the book. Okay, if you go to the end of the book, for every pure component at convergence pressure, I believe 5,000, the values of Kj is given for any pressure and temperature. So here is an example. So this is for propane. So for convergence pressure of 5,000 psi, for a mixture for the pure component propane at any pressure, so the x-axis is pressure, I can read the K value at any different temperatures. So here on these graphs, I have the temperatures. So let's say if the temperature is, let's say, minus 60 degree Fahrenheit, and pressure is, let's say, so this is 10, this is 100, this is 300, 400. Let's say if it's 400 psi and minus 60 degree Fahrenheit, I can read the K value, and that K value is, here is 0.01, 0.02, 0.03, 4, 5, 6. So I can read that value at 0.04 or 0.05, okay, as a value of K for a propane at 400 and minus 60. If the temperature is 200, pressure is 1,000, so at 1,000 I draw a line all the way to 200, and then I read this value. So this is 0.1, so it becomes around 0.8. So for any pure component like propane, for any pressure and less certain temperature, the K values can be obtained from the end of the book. So I pick any one of these equations. If I'm going to write for mole fractions of the liquid, I'll pick equation 1217. The Zj is given, Kj I read from the end of the book, I assume an Ng value, I repeat that assumption, I do assume two values, and then I do the linear interpolation, and I will get the exact number. So let's look at the example. So example 12.4. So this might be very similar to your final exam open book question. So it says, calculate the compositions and quantities of the gas and liquid when 1 pound mole of the following mixture is brought to equilibrium at 150 degree Fahrenheit and 200 psi. Do not assume ideal solution. So you don't assume ideal solution except if the question tells you that's ideal solution. Okay, so if it doesn't say anything, you must assume that's a real solution. So again, the mixture is given, so propane and butane and pentane. The composition of the mixture is given. So to find, here I'm going to use the equation for the summation of the gas. So I'm going to use 1218. So if I use 1218, the Zj is given. These are the composition and the mixture. NL I don't know, I need to guess. Kj. So for every component at the temperature of 150 and pressure of 200 psi, I need to go to the end of the book and read the K value and then plug it here. So for example, here for the case of propane, the temperature is 200, the temperature is 150, and the pressure is 200. So 200, this is 100, this is 200, so this is 200. I draw a line, okay. This is 100, this is 120, this is 140, so 150 is somewhere here. So I can draw a line. So the K value is around, let's say, 1.5 roughly. Okay, that's the K value that I can read. So see propane, the K value, the exact number is 1.55. So if you use the rulers, definitely you will get a much better estimate than I do. So it's very simple. You just have the component, you have the pressure and temperature, you go to the end of the book, you read the K value. So for every component, I'm going to read the K values. Okay. So the ZJs were given, the K values I read from end of the book. One important point is, we know all these components, they belong to the same homologous series. So the properties should be, we should be able to infer the properties. We should be able to see the trend in the properties. So if you're looking, if you're reading the K value and you read the first number to be 1.55, the second number to be 0.59, the third number cannot be like more than 0.59, cannot be like 0.6, because I see the trend is decreasing. It's like 1.5, 0.5, 0.6, and then the next one is 0.2. So you can look at this and see if you have like 1.5 and 2 and then 0.8, definitely you are reading one of these numbers wrong, okay? So this is just a checkpoint, okay? So make sure if the trend is decreasing, it has to be decreasing for all these numbers, okay? Or if it's increasing, then it has to be increasing. So we have the K values from end of the book. So here we are going to make the first guess. As I said, let's say it's NL is equal to 0.5. So if you assume NL being 0.5, so you have the ZJ value given, NL you assume 0.5, and K value you just read from the chart. So you can calculate this ratio of ZJ over 1 plus NL times 1 over KJ minus 1 for every single component. That would be the gas composition. Okay, so you calculate them, you sum them up. It's 0.992. Again, 0.992 is not 1. Okay, so your NL, even though it's very close, but it's not exact. So NL being 0.5 is not the correct NL value. So because the summation didn't add up to 1. So I need to make another guess. So for the next guess, let's say I assume 0.6. Okay, if I assume 0.6, again, now ZJ again given, KJ the same, you read from end of the book, you already have it. This time you assume NL to be 0.6. So if you put NL being 0.6, do the calculation, the summation becomes 1.01. Again, 1.01 is not equal to 1. So we have two guess values. For NL of 0.5, summation is 0.99. For NL of 0.6, the summation is 1.01. So I can write the equation for the straight line passing through these 2 points, and then I can say for what x, the y becomes equal to 1. Because this equation tells me the summation is equal to A times number of NL plus B. If I find that, then I would say for what NL, the summation becomes equal to 1. And if you do that, the value becomes 0.547. Basically, you're doing linear interpolation. So NL being 0.547, if you plug in, the summation becomes exact 1. So if NL is 0.547, NG is 1 minus 0.547. Okay, so I will have the number of moles in liquid, number of moles in gas, which is 1 minus that. These are the composition of the gas. So the composition of the liquid becomes the composition of gas divided by Kj. Remember, the Kj was Yj over Xj. So if I have the mole fraction of the gas, which is here, mole fraction of the liquid is simply Yj, these numbers divided by Kj's. So I can find the composition of the liquid. So I can get the composition of gas, composition of liquid, number of moles in liquid, and number of moles in gas, which is 1 minus this number. Okay, so it's very simple. The composition of a mixture is given. For every component, you need to go to the end of the book, read the K values, and then make two assumptions for NL value. And then do the linear interpolation, find the right NL. The NL, which gives you the summation of gas composition, the gas being equal to 1, is giving you the composition of gas in the composition of the gas. And then you can use this composition of the gas to find the composition of the liquid by simply dividing that by Kj. Okay, so this is a potential open book question. As I said, either finding the composition and quantities of the gas and liquid in a mixture, very similar to example 12.4, or